Hello again. My name is Michael Zuccaro, and I'm going to be pitching some projects to focus on having stable haploid human stem cell populations. So a quick recap, I didn't realize how back-to-back this would be, so I don't think anyone really left. But we developed these haploid human stem cells. They're pluripotent, and you can essentially look at the genome functionally through different types of cells that are differentiated through these cells. And this would be a powerful tool for GP Write, having essentially half the genome that you'd have to work with. But the main challenge that we face, the main obstacle, is that early on especially, there's this spontaneous diploidization that prevents us sometimes from isolating haploid cells. And then we constantly have to do FAC sorting to purify for this haploid population. So we sought to look early on at what point during the so-called development of these cells does the diploidization take place. So one of the OBGYN fellows and myself independently, we did the centromere staining that I mentioned before, and we pooled our data, and it looks like, even though you can see as early as the cleavage stages, which is those 2, 4, 8 cell stages in development, at the blastocyst stage, where I showed before that ICM that you isolate to get the actual stem cells, that's really where we're seeing a lot of the diploidization. And so I have this movie, which is a bit hard on the eyes, I apologize, but again, laser pointer. So there's a cell right here, a single cell, and that's going to divide, and if you can track it, it's right here, and as it divides, it kind of splits, but it doesn't actually separate, because you can see then it comes together again, and both nuclei take part in that same division, and you get this pyramidal structure at the end of the video. And so looking into the literature, because I hadn't seen this before, this is indicative of multipolar cell division. So typically when you have a cell dividing, duplicates its centrosome, they travel to different ends of the cell, and they create that bipolar division that we all are aware of. But what happens if you have more than those two, you'll get pulling from different ends, and you get these asymmetric, either like this pyramidal or a cruciform kind of structure. And again, doing the centromere counts, which is how we identify haploid versus diploid, I noticed a lot of these structures. So here was another one. And also with a lot of these, there's a huge amount of centromeres. So this one I think had something like 300. So we were curious, maybe this is something that's related to the diploidization, this cytokinesis. So again, this is the multipolar division that's happening. So we've got here a regular haploid cell. The chromosomes have been duplicated. It's ready to divide. The centrosomes are going to start moving. And then we have a diploid cell, which actually, if you can see, has 4 centrosomes. And again, this abnormal, it's already starting to do an asymmetric multipolar division, it looks like. So I think I've almost time's up. So real quick, almost verbatim, a few aims, a few projects we want to do. First, determine the consequences of gene editing and multiple rounds of FAC sorting. As I mentioned before, the hoax dye, you need UV radiation to look at these through exome sequencing. And aim 2, understand diploidization pathways. So we think that there's a failure in cytokinesis, which is responsible for this. We're going to do live cell imaging. I have the cells that you saw before were GFP in the H2B region. And so we're also going to be looking cherry and H2B in centrosomes, centromeres, and really building that up. It's still early on. And then transcriptome analysis of haploid versus diploid versus tetraploid cells and seeing if there's a difference there. And then trying to actually get these haploid cells to become more stable and resist diploidization. So looking at the centrosomes and maybe inhibiting something like centrosome clustering, which is how these cells can maybe bypass death through asymmetric division. And lastly, derivation of additional haploid cells, both androgenetic and parthenogenic, employing all of these so that hopefully we can get from early on a nice set of haploid cells and then continue from there and show that this would be a feasible way to go. So with that, thank you.